So, good day, Doctor. Today we're going to discuss about our buckling analysis for thin plates. And to begin with, we will introduce ourselves. My name is Kenneth Bernes Kutat, and my metric number is 195667.
My name is Jubair Abdullah Rafiul Alam, and my metric number is 195734.
And my name is Yusuf Abdullah Salah, and my metric number is 195567.
My name is Jamila Suhaila, and my metric number is 195467.
Okay, I will start with the introduction. The introduction is there is 3 points. The first point is buckling is a sudden deformation of the structure component under the compressive load. If the load continues to increase, the structure member may experience sudden change of the shape. The second point is there are 2 types of buckling, elastic buckling and inelastic buckling. Elastic buckling will go back to its original position, while inelastic buckling will not go back to its initial shape. The third point is buckling occurs at buckling stress of critical stress that is below the limit of proportionality. The critical stress value is vital to ensure that even at buckling loads, the stress inside the material is still lower than yield strength of the material. In other words, above the critical stress, buckling will occur, while below the critical stress, buckling will not occur. Now we will pass it to Rafi. Start with analysis.
Thanks, Yusuf. So now we're moving on to analysis. So as it can be seen, the figure 1 shows the stiffened panel wing section for Bombardier Dash 8-400. And for this analysis, the material was treated as thin plates for the calculation of buckling coefficients. The boundary condition stiffened panel was assumed to be both fixed, and the thin plate was assumed after initial buckling. The stress in the plate increases parabolically from its critical value in the center of the section. So as it can be seen from the table, the table 1 shows the sectional properties for 2024 T2 aluminum alloy. So the length of the aluminum alloy component is 0.3952 meter, and the base B is 0.7163 meter, and we have skin thickness as denoted as TSK 0.08 meter, and so on and so forth. So let's move on. Okay, so figure 2 shows the buckling of a thin plate, and to determine the buckling coefficient K, given value A over B was defined first. So in our case, A is 0.5 meter and B is 0.7104 meter. So we get A over B as 0.69907. So by calculating the A over B, we need to determine our K value. So using figure 3 as a reference from Maxon book, so we assume that we used both unloaded edges simply supported. So from the graph, we can assume for our A over B is 0.69907. So if you input that in the graph, we can assume that the K value is almost 6. So we assume that our K equals to 6. Okay, so let's move on. Okay, so table 2 shows the variation of boundary conditions. So there are different type of boundary conditions such as both pinned, both fixed, one fixed, the other free, one fixed, the other pinned, etc. So in table 2, from the Maxon book, the solution in terms of effective length LE for columns having a variety of end conditions. In our case, the boundary condition was assumed to be both fixed. So the effective length was LE over L equals to 0.5. As it can be seen from the table, both fixed. LE over L is 0.5, where V is 0 and Z equals to 0 and Z equals to L, and dV over dZ is equals to 0 at Z equals to L. So if we calculate LE, we get LE equals to 0.5 L is equals to 0.5 times 0.3952 meter. So LE, we get 0.1956 meter. So the next part of the presentation will be continued by Glenn. Thank you.
So today I'm going to discuss about the detailed calculation of our cross-sectional T-section dimension. So on the left side figure denoted the different symbols. We have Y1, which is the half with respect to center of the stiffened panel. Y2 is the center of the skin, and the thickness was assumed to be constant across all sections. So the buckling analysis was uh, was comprised buckling part by part analysis. And to begin with, we calculated the cross sectional of the section. So we first obtained the cross sectional of the uh, stiffened panel and the skin. So once we have the sum of those sections, we can get the total area of the cross sectional of the T section. So we arrive at 8.89 times 10 to negative 2 m squared. So next, we tried to calculate the first moment of area, or the y bar. So using this by taking the moment of with respect to the sign chart of the whole section. So after deriving the formula, we can get the y bar to 0.0960 meter. So that's the distance between the full centroid of the whole section. So next, we calculate the second moment of inertia. So for this part, we use the second moment of inertia for the skin with respect to its centroidal axis. However, for the stiffener, we comprises two regions: stiffener at the top and stiffener from the bottom. So we calculate with respect to direct axis, both from the top and the bottom. So which means that the moment of inertia will differ from the formula with respect to their axis or the centroidal. So in this case, once we got the total second moment of inertia for these regions, we got a total of 7.88 times 10 to negative 4 m4. So next thing, once we got the moment of inertia, a second moment of inertia, we can obtain the radius of gyration with respect to the cross-sectional area of the T section. So we arrive at 9.42 times 10 to negative 2 m. So once we got the radius of gyration, we can calculate the slenderness ratio. So we arrive at 2.076, which is relatively small. Um, by intuitively, we can expect a high critical stress since we have a low slenderness ratio. So in this case, n was assumed to equal to 1. So buckling was affected by the boundary condition of the column, which was both fixed. So from equation 8 from Megson's textbook, we arrived, the book derived a critical stress formula for the panel only. So since I mentioned the buckling analysis will be part by part analysis, so in this case, we have a panel, stiffener, and a skin. So in this case, for each section, there is a distinct critical formula for each critical stress. But in this case, for panel, the critical stress will vary, is dependent for the slenderness ratio. But for others, it depends on other dimension. So in this case, for the critical stress, for the panel arrived at 167.33 GPa. And Next thing, we also accounted the equivalent thickness of the section so that we can get the overall buckling of the panel. So in this case, the equivalent thickness, we arrive at 1.24 times 10 to negative 1 meter. And for the overall buckling of the panel, we arrive at that of 20.74 times 10 to 9 Newton per length or Newton per meter. So next thing is we get the buckling critical stress of the sheet or the skin. So here we accounted the Poisson's ratio, the skin, and the base of that section. So for the critical stress of the skin or the sheet, we have a 62.95 GPa. And by manipulating or by deriving it from the previous equations, we can get the over buckling of the sheet around 7.69 times 10 9 Newton per length. And next is stiffener, and this is the same as the formula from our critical stress, which is from the skin. So for this case, we arrive at 144.09 GPa. And by that, we can use the equivalent thickness multiplied by the critical stress of the stiffener, we can get the overall buckling. So we arrive at 17.86 times 10 to 9 Newton per length. So in this case, it will be discussed by my colleague, which is Wala, for the summary of my calculations.
Okay, I'm going to discuss about the discussion of the analysis and the recommendation. So here we have the table of critical stress and overall buckling, how it varies with the different sections. For the panel, sheet, and stiffener, we have the values for critical stress and overall buckling. We can see that the lowest value of critical stress and overall buckling is we get that from the sheet or the skin. Compression member is usually subjected to two modes of failure: elastic buckling and inelastic buckling. In our case, we have the critical stress, which is greater than the yield stress, and that's why our material deform plastically, and also like it still retains the shape when the force is removed, and hence we have the inelastic buckling. So let's move on to the recommendation. For the recommendation, we can see that we have the graph, which is the critical stress versus slenderness ratio graph. And also we can see that as slenderness ratio increases, the critical stress decreases and vice versa. Based from this graph, we can predict on how to minimize the buckling load before the proportional limit as well as the compressive strength. For this reason, this is to ensure the structural member will undergo an elastic buckling when the lateral force is removed to return its original shape. And also, like if we want to keep our material in the elastic region, what we can do is from the graph, we can we can actually observe, we can actually note how can we increase the slenderness ratio or decrease the slenderness ratio. We have to change the slenderness ratio in order to keep the material in elastic region. So from the graph, we can predict that our slenderness ratio must be greater than 48.8127 to remain in the elastic region. And yeah, in our case, the slenderness ratio was 2.076 and the critical stress was 163,598 megapascals. And based from these values, the critical stress exceeded the yield and compressive strength. So we have to increase the rib spacing to increase the slenderness ratio to be, in order to be greater than the slenderness ratio limitation, which is 48.8127. That's the optimum slenderness ratio. That's it from us. Thank you.